Hi, welcome to Chapter 6. It's Masonry Chimneys. This is our third part of Masonry Chimneys. Hope you enjoyed the video. The first 5 minutes is free. If you want to purchase the whole video, it's in the links. If you want to purchase the whole series, it's also in the links. Enjoy. Thank you very much. Have a good day.
Another essential measurement is the distance from the top of the fireplace opening to the base of the damper, which is called the throat. This vertical distance acts as the initial smoke reservoir and plays a major role in shaping the airflow pattern as the smoke exits the firebox. According to IRCR 1016, this distance must be a minimum of 8 inches for standard fireplaces. Rumford fireplaces, known for their tall, shallow, highly efficient design, require a minimum of 12 inches because they rely on a different aerodynamic profile to accelerate draft and push smoke into the flue. This throat clearance is one of the most important dimensions in the entire fireplace system. If the throat is too close to the opening, smoke has insufficient space to turn upward, resulting in turbulence and smoke being pushed into the room. People in the fireplace industry understand that this dimension is fundamental to preventing smoke spillage, and that correcting this distance is often key to solving chronic smoking problems in older or improperly built fireplaces. In some cases, this minimum throat distance can be effectively improved by installing a smoke guard. A smoke guard is a metal strip mounted across the top portion of the fireplace opening, reducing the vertical height of the opening by approximately 4 to 6 inches, sometimes more. By decreasing the opening height, the smoke guard improves the draft geometry between the firebox and the throat, helping reestablish a proper smoke path. The guard essentially forces smoke to rise more sharply into the throat instead of rolling forward into the room. Smoke guards are often used as a practical fix for fireplaces that were built with openings that are too tall or for fireplaces that smoke occasionally due to marginal throat geometry. Taken together, these measurements, the fireplace opening, the firebox depth, the throat height, and the liner cross-section, provide a complete picture of how well the fireplace is engineered to draft properly. When these dimensions are correct, the fireplace operates smoothly. When one or more of them are incorrect, smoke, odor, and performance problems almost always develop. One of the most important topics to understand and to explain clearly is why firebox mortar joints fail and what the building code requires to prevent that failure. The International Residential Code addresses this directly in IRCR 1015, which establishes the structural and material requirements for firebox walls. Under R1015, firebox walls must be 8 inches thick when lined with firebrick, or 10 inches of solid masonry if there is no firebrick lining at all. This is to ensure that the firebox contains the extreme heat generated during use. However, simply having thick walls is not enough. The code also places special requirements on the mortar joints inside the firebox, limiting them to a maximum of 1/4 inch and requiring the use of refractory mortar. These requirements exist for a very specific reason, and understanding the science behind them is essential for anyone working in the field. Standard Portland cement mortar, which is used in general masonry construction, is not compatible with fireplace temperatures. Portland cement begins to lose structural integrity when repeatedly heated and cooled, particularly when temperatures fall below about 700 degrees Fahrenheit during the cooling cycle. Inside a firebox, the mortar joints are subjected to repeated extreme temperature swings. They may reach hundreds of degrees during a burn and then cool rapidly afterward. Each heating and cooling cycle causes Portland mortar to expand, contract, and chemically weaken. Over time, it becomes brittle, cracks, and eventually crumbles out of the joints. This is why so many older fireplaces show missing or deteriorated mortar. The wrong material was used. Refractory mortar, by contrast, is designed to withstand the intense heat inside a fireplace. It contains high-temperature ingredients such as fireclay and calcium aluminate, allowing it to remain stable at temperatures far higher than those encountered in typical residential fires. It does not break down during repeated heating and cooling cycles, which makes it the correct material for firebox construction. The 1/4 inch maximum joint thickness is equally important. Thick joints hold more mortar, and more mortar means more expansion and contraction. This increases internal stress and accelerates failure. Thin joints minimize the volume of material exposed to thermal shock and help the firebrick and mortar behave as a unified, stable lining. When teaching this subject, the key takeaway to emphasize is simple. Firebox joints fail because Portland mortar cannot survive fireplace temperatures. That is why the code requires refractory mortar and limits firebox joints to 1/4 inch. Combined with the mandated wall thickness of 8 or 10 inches under our 1001-5, these rules ensure the firebox can safely handle the intense thermal environment it is exposed to. As we continue taking measurements in the fireplace, one of the next areas to evaluate is the outer hearth. The size of the hearth extension is determined by whether the fireplace opening is smaller or larger than 6 square feet. To determine this, the width and height of the fireplace opening are multiplied to find the total square footage. Fireplaces with openings under 6 square feet require a smaller hearth extension, while those with openings 6 square feet or larger require a larger one. If the opening is under 6 square feet, the hearth must extend at least 16 inches in front of the opening and at least 8 inches to each side. When the opening is 6 square feet or more, the extension increases to 20 inches in front and 12 inches to each side. These dimensions are important because they protect combustible flooring from radiant heat, embers, and sparks that may escape the firebox. Another important part of the inspection is measuring the mantle and any combustible trim located above the fireplace. The mantle must be positioned high enough above the opening so that it cannot overheat. The code requires a minimum clearance of 12 inches between the top of the fireplace opening and the bottom of a combustible mantle. At 12 inches above the opening, the mantle is not allowed to project outward at all. Once the mantle is positioned higher than 12 inches, it may project outward 1 inch for each additional inch of vertical rise above the opening. For example, trim cannot be within 6 inches of the fireplace opening. Between 6 and 12 inches, it can protrude 1.5 inches from the face until it reaches 12 inches above the fireplace opening. Combustible mantle is far enough away from the firebox, more than 12 inches in every direction. The amount it protrudes outward no longer matters because the heat exposure at that distance becomes insignificant. It is important to emphasize that accurate measurements of the hearth extension and mantle clearance directly affect fireplace safety. Larger openings require deeper hearths to protect against escaping embers, and mantle height directly influences how much heat the wood trim will be exposed to. Understanding these relationships allows inspectors and technicians to verify whether a fireplace meets code and ensures that it will perform safely for the homeowner. As the interior inspection continues, attention should move to 3 key areas: the ash dump door, the profile seams, and the lintel collar joint. Each of these components plays an important role in containing heat within the firebox and preventing unsafe heat transfer into surrounding combustible materials. The ash dump door is located at the base of the firebox floor, usually toward the rear, and provides a passage for removing cooled ashes into an ash pit below. If this door becomes warped, cracked, or fails to close tightly, it can allow hot embers to fall through instead of cold ashes. This is dangerous because embers can ignite debris in the ash pit or cause heat buildup in areas not designed to withstand high temperatures. A properly functioning ash dump door should close securely and remain flush with the hearth surface. Next, the inspector should examine the profile seams along the sides of the fireplace. The profile seam is the vertical joint where the firebox walls transition from the firebrick-lined interior to the surrounding masonry structure. In many fireplaces, this seam exists where the inner firebrick shell stops and the outer masonry begins. If the collar joint of the seam becomes deteriorated or develops gaps, heat can escape sideways from the firebox and transfer directly into the side walls of the fireplace structure. If these walls contain wooden framing or other combustible components, excessive heat transfer may lead to charring or ignition over time. Maintaining these seams with refractory mortar is essential to keeping high temperatures confined within the firebox where they belong. Equally important is inspecting the lintel collar joint, located at the top of the fireplace opening where the steel lintel supports the brickwork above. The lintel spans the opening and creates a narrow joint between the firebox structure and the masonry or framing above the fireplace opening. If this lintel joint deteriorates or opens, heat and flames can escape upward behind the mantle area. The wall immediately behind the mantle often contains wood framing, which can be exposed to dangerously high temperatures if the lintel joint has failed. Even moderate heat over long periods can pyrolyze wood, lowering its ignition temperature and presenting a hidden fire hazard. Together, the ash dump door, the profile seams, and the lintel collar joint form a thermal boundary designed to confine heat inside the firebox. Any damage, warping, or deterioration in these areas compromises this boundary and allows heat to reach parts of the structure that were never intended to withstand fireplace temperatures. Inspectors must check these areas closely, ensuring that the firebox remains sealed, stable, and safe for continued use. The next component to examine during an interior fireplace inspection is the damper, which plays a critical role in controlling airflow, drafting performance, and heat retention. There are several different types of fireplace dampers, and understanding how each operates makes it easier to identify defects and determine whether repairs or replacement are needed. A poker damper is the simplest style and is operated manually using a metal rod or poker that pushes or pulls the damper plate into the open or closed position. These dampers are typically found in older fireplaces and are prone to rusting or seizing because they rely on exposed metal components. A rotary damper uses a rotating handle inside the firebox to turn a shaft connected to the damper plate. As the handle turns, the plate pivots, open or closed. This type is more mechanically refined than a poker damper, but still vulnerable to corrosion and soot buildup around the moving parts. A ratchet damper operates with a notched mechanism that allows the damper plate to lock into several partially open positions. As the handle is lifted or moved, it engages the notches to hold the plate at the desired draft setting. These systems can wear out over time, causing the damper to slip or fail to hold its position. A top sealing damper, installed at the top of the flue rather than inside the firebox, acts both as a damper and a chimney cap. It seals tightly with a gasket and is opened from inside the fireplace by pulling a cable. Because the top sealing damper closes at the top of the chimney, it prevents heat loss, downdrafts, moisture intrusion, and animal entry far more effectively than interior dampers. It is a popular upgrade when traditional dampers are rusted or missing. Regardless of the damper type, inspectors should look for rust, deterioration, warping, misalignment, or operational malfunction. Dampers often experience heavy creosote accumulation, moisture exposure, and corrosion from condensation. Any deterioration can restrict draft or prevent the damper from sealing properly. During this stage of the inspection, it is often recommended to remove the damper plate for a more thorough evaluation. This is typically done by removing the cotter pin that holds the damper in place. Once the cotter pin is taken out, the plate can be lowered and removed, allowing a clear view of the smoke chamber, throat area, and damper frame. It is a best practice to carry replacement cotter pins on your service vehicle so that the damper can be reassembled properly after inspection or cleaning. Inspecting the damper carefully ensures that the fireplace drafts correctly, prevents unwanted heat loss, and maintains safe operation. Regular removal and evaluation of the damper plate also make it easier to detect hidden issues in the smoke chamber and throat that might otherwise be missed. The next area to inspect during an interior fireplace evaluation is the smoke chamber, which is one of the most important and most regulated parts of the entire chimney system. The smoke chamber is the transitional space between the firebox and the flue, and its shape, thickness, and construction have a significant impact on draft, safety, and heat containment. The requirements for this area are clearly outlined in IRC R1001-8, and understanding these details is essential when teaching proper inspection procedures. According to R1001-8, the smoke chamber walls must be 8 inches thick on all 4 sides, unless a listed liner system is used that provides equivalent protection. This thickness ensures that the structure can safely contain the high temperatures and turbulent airflow generated as smoke transitions from the fireplace opening into the chimney flue. Because the smoke chamber experiences intense heat and rapid temperature changes, insufficient wall thickness can lead to cracking, heat transfer into combustibles, and long-term structural failure. The code also requires that the interior surfaces of the smoke chamber be parched smooth with refractory mortar. This is not merely a cosmetic requirement. Smooth refractory parging eliminates ledges, gaps, and brick projections caused by corbelled construction. These rough surfaces disrupt airflow, create turbulence, trap creosote, and significantly reduce draft efficiency. Refractory mortar also acts as a thin insulating layer, helping to contain heat inside the smoke chamber and reducing thermal stress on the surrounding masonry. Another key requirement in R1001-8 is that the top of the smoke chamber must support the flue on all 4 sides. The flue liner should rest fully on a complete masonry ledge, not on partial support or suspended edges. Proper support prevents flue tiles from cracking, shifting, or collapsing over time. Unsupported flues can settle unevenly, create gaps, or break free from the smoke chamber structure, all of which compromise the safety of the system. The code also limits the height of the smoke chamber, stating that it may not be taller than the width of the fireplace opening. This prevents excessively tall smoke chambers, which would disrupt draft and create zones of stagnant air or backflow. Maintaining the correct proportions ensures that smoke funnels smoothly upward into the flue without billowing outward into the room. Finally, if the smoke chamber is constructed using corbelled masonry, the code requires that it shall not slope more than 30 degrees from vertical. Corbelling is the traditional method of stepping the walls inward to meet the flue liner above. If these steps slope too sharply, they create severe turbulence and unnecessary heat concentration. Keeping the slope within the 30-degree limit ensures proper airflow and reduces the risk of cracking from thermal stress. Technicians need to evaluate the smoke chamber according to these IRC provisions is vital. A properly constructed smoke chamber with thick walls, smooth refractory parging, full flue support, and correct angular construction is essential for safe and efficient drafting. A poorly built smoke chamber, by contrast, is one of the leading causes of smoking problems, creosote accumulation, and heat transfer hazards in masonry fireplaces. When the inspection reaches the point where visibility becomes limited, the next essential tool is a selfie stick with a phone or small inspection camera. This allows us to see critical areas of the fireplace and chimney that cannot be viewed from below. With this tool, there are two key locations we focus on: the smoke shelf and the lower portion of the flue liner where it rests on top of the smoke chamber. The first location to inspect is the smoke shelf, which sits behind the damper and below the smoke chamber. Using the selfie stick, we look for several issues. One of the most common problems is dead animals, since raccoons, squirrels, and birds often fall down the chimney and become trapped on the shelf. Another issue is creosote buildup, especially when the smoke shelf has been improperly constructed as a hollow cavity. This hollow space can accumulate soot and creosote, leading to potential chimney fires and drafting issues. Some masons leave the area behind the firebox wall hollow because IRC figure R1011 fireplace and chimney detail appears at first glance to show that space is open. However, this is a misunderstanding of the figure. That area should never be left hollow. It must be completely filled with grout mixed with fire clay. Properly filling this space serves several important purposes. First, it eliminates a hollow void where creosote can accumulate or animals can nest. Second, the bottom of the smoke shelf should be curved upward, creating an aerodynamic contour that redirects downdrafts from the chimney and helps promote upward air movement. This curved, solid smoke shelf improves draft performance and reduces the likelihood of smoke being forced forward into the room. Finally, grouting this cavity adds structural strength to the rear firebox wall, preventing cracking, bowing, or movement under high heat. The next step is to raise the selfie stick camera up through the smoke chamber to inspect the area where the chimney liner sits on top of the smoke chamber. This is one of the most important parts of the inspection because it verifies whether the flue liner is properly supported on all four sides. As required by code, the liner should rest fully on the top of the smoke chamber walls. If the flue is not supported, if it is floating, or if gaps are present, the liner may settle unevenly, fracture, or lean over time. This can create gaps between liner tiles, misalignments, and heat transfer hazards. With the camera, we are also able to observe the condition of the lower end of the flue liner, looking for cracks, missing mortar joints, or signs of thermal damage. Using a selfie stick to inspect both the smoke shelf and the liner support area provides essential information that cannot be obtained from ground-level viewing. These two locations are among the most critical for diagnosing drafting issues, structural weaknesses, and safety hazards within a masonry fireplace system. As we conclude our discussion of chimney components, the underside of the outer hearth is one last area that must not be overlooked. Although it is rarely visible during day-to-day use, it is an important structural and safety-related element of a properly constructed fireplace system. The outer hearth, the portion that extends into the room in front of the firebox, is typically made of cast-in-place reinforced concrete. During construction, this concrete is usually poured over a temporary plywood form. Once the concrete has cured and gained adequate strength, the plywood or any other combustible forming material is supposed to be removed. Leaving combustible materials attached to the underside of the hearth is a direct violation of the building code and creates an unnecessary fire hazard.